Okay, reflection, refraction, dispersion, diffraction, and now interference. And I am going to illustrate the idea of interference, which you already have some familiarity with, using one-dimensional springs, as a two-dimensional system with a ripple tank having sources, point sources, making a disturbance, like here, making a disturbance, making these circular wave fronts. That's source 1. And then we have source 2 right next to it. I'm showing them independently here, source 1 off, source 2 on, making independent circular wave fronts. When they interfere with each other, they will be superimposed on each other. They'll obey the laws of superposition that we've already seen. Now, the wave energy is constant along the circular fronts as well. And all right, so you can think of those as constant energy locations. And there's greater potential energy, for instance, when the crest, when you're along the crest, because the crest is the maximum displacement of the medium. And then at the equilibrium, there's more kinetic energy, if you recall that idea. Both sources on. We have both of the circular wave fronts, and they're superimposed on each other. Now, of course, when they cross, remember, these are, highest amplitude locations. The crest is the peak of the wave. So when a peak meets peak, when you see these crossing points, you know that they should be adding to greater amplitude. So I'm going to draw lines here that connect these crest overlaps. And these are regions where the wave amplitude is maxed out. These are the antinodes. The antinodes. We have the highest amplitude. Halfway in between those, now it's harder to see in this little graphic, but halfway in between the antinodes, you already know those are the nodes. And it's like they're equal spacing between each one of these things here. Happens to be where they're canceling. So these are cancellation regions, or nodes, where the medium doesn't move. So regions of maximum wave energy, they're called antinodal lines. Antinodal lines. You just see a line along here of antinodes. No wave energy, nodal lines. They tend to be darker. So hopefully I can illustrate that for you. But hopefully the basic idea makes sense here. Now, what does the nodal line pattern depend on? You could even say antinodal line. But what makes that pattern change? Well, let's vary the wavelength. Vary the wavelength of these circular fronts. So I'm going to make them farther apart or closer together, but a constant separation distance between them. Constant D, constant distance between the sources. All right, in this case, we're going to have long wavelength. And we have long wavelength. We see these nodal lines, the dark lines at least, kind of like this. And if it's short wavelength, we see a heck of a lot more. So we have more, I guess you could say, more interference going on, so to speak. So short wavelength, high frequency. So we vary the distance. We vary the distance between these two, but keep a constant frequency or wavelength. It's going to look like this. When they're close together, you're going to see not much, not many nodal lines or antinodal lines. When they're spaced far apart, then you end up seeing a whole lot. Okay, and it has to do with the distance between the sources, allowing for this overlap to happen. When they're really close, if you imagine the circular regions real close to each other, you don't get very many places where they're overlapping. All right, so that's a little bit hard to visualize at the moment, but seeing it in the ripple tank will bring that into a lot more clarity. So that is That is the interference pattern produced by circular waves. Conclusion, the lambda over d small, you have many lines. Lambda over d large, just a few lines. Okay, so this is lambda over d small means small wavelength, large distance. Small distance here with wavelength large is going to result in just a few lines. Okay. All right, well, that'll wrap up our basic intro to the parameters of these wavefronts, and we will enter into a study of sound going forward.